On October 29th, 2025, an interstellar comet did something that defies everything we know about how comets behave near the sun. It turned bluer than our star itself. Understanding what happened during those crucial hours could rewrite our models of interstellar space, reveal entirely new physics of solar interaction, or confirm we've witnessed the rarest cosmic phenomenon of our generation. Multiple spacecraft SOHO Stereo A and GOES 19 captured the impossible. A comet brightening so rapidly it outpaced every prediction, glowing with colors that shouldn't exist at those temperatures. But how can frozen debris from another star system become bluer than the nuclear furnace heating it? And why did this happen at the exact moment we couldn't watch from Earth? Tonight, we're diving into the most thoroughly observed yet deeply mysterious interstellar visitor ever recorded. This isn't speculation. This is documented, peer-reviewed science that nobody can fully explain. Over the next 2 hours, we'll examine what happened when 3I Atlas swung around our sun, why it behaved in ways that challenge our understanding of comets, and what this visitor from beyond our solar system might reveal about the universe we inhabit. This is a story about the limits of human knowledge, the patterns we see in chaos, and the profound question that keeps astronomers awake at night: if something extraordinary passed through our solar system, would we even recognize it? Let's begin at the beginning with a discovery that would captivate the world. July 1st, 2025, Rio Hurtado, Chile. The Atlas Survey Telescope, Asteroid Terrestrial Impact Last Alert System, was doing what it does every clear night, scanning the heavens for anything that moves, anything that doesn't belong, anything that might threaten Earth. At 4.5 astronomical units from the Sun, farther out than Mars beyond the asteroid belt, the automated system flagged a faint, fast-moving object. Initial calculations showed something immediately remarkable. This object wasn't orbiting the Sun, it was passing through. The orbital eccentricity came back at approximately 6.1. Any number above 1.0 means an object is on a hyperbolic trajectory, not gravitationally bound to our star. This visitor was just passing through our cosmic neighborhood, a traveler from the space between stars. Within days, observatories around the world turned their instruments toward this new arrival. The designation was assigned C2025N1, but it would become known by a simpler name that carried enormous significance: 3I Atlas. The 3I designation means interstellar object number 3. Think about that for a moment. In all of human history, in all our centuries of watching the skies, we've only confirmed 3 objects from beyond our solar system passing through our space. The first was Oumuamua in 2017, a tumbling, elongated mystery that we barely glimpsed as it departed. The second was 2I Borisov in 2019, a more conventional-looking comet that gave us our first real opportunity to study interstellar material. Now came 3I Atlas, and this one was different. Early measurements revealed an object traveling at 68 kilometers per second relative to the Sun. To put that in perspective, that's about 240,000 kilometers per hour, roughly 150,000 miles per hour. It's moving twice as fast as the previous interstellar visitors. At that velocity, it crosses the distance from Earth to the Moon in less than 2 hours. Consider what that speed means in human terms. If you could somehow stand on 3I Atlas's surface, you would circle the Earth's equator in less than 10 minutes. You would travel from New York to London in about 20 seconds. The velocity is so extreme that if the comet were to somehow strike Earth, which it won't, but imagine the kinetic energy would be biblical in scale. Mass times velocity squared. The mathematics of destruction are sobering. But more interesting than the destructive potential is what this velocity tells us about the comet's history. Objects don't naturally achieve such speeds within a single star system. Something accelerated 3I Atlas, perhaps a close gravitational encounter with a giant planet slingshotting it outward. Perhaps its parent star went supernova, the explosive shockwave hurling debris into the void.
Perhaps it was born in a dense stellar cluster where gravitational interactions routinely eject objects at extreme velocities. Whatever the mechanism, 3I Atlas has been traveling for a very long time. At 68 kilometers per second, it would take roughly 20,000 years to travel 1 light year. The nearest star to our Sun Proxima Centauri is 4.24 light years away. Do the math: about 85,000 years minimum travel time, assuming the comet came from the nearest possible origin. But it probably didn't come from Proxima Centauri. The trajectory doesn't point back that direction. Working backward through galactic space, accounting for stellar motions and gravitational perturbations, researchers can only trace the path back about 10 million years before uncertainties overwhelm the calculations. 10 million years of travel. During that time, humanity's ancestors were still learning to walk upright. The continents were in different positions. The climate of Earth was alien to modern eyes. And through all those millennia, 3I Atlas was drifting through the darkness between stars frozen dormant waiting. Until July 1st, 2025, when a telescope in Chile noticed something moving against the background stars. But speed wasn't the only unusual characteristic. The trajectory calculations showed something that made astronomers pause. The comet's path lay within 5 degrees of the ecliptic plane, the flat disk where all the planets orbit the plane that defines our solar system's architecture. If interstellar objects arrive from random directions, the probability of one aligning this closely with the ecliptic is roughly 0.2%. 1 in 500. Not impossible, but definitely enough to raise eyebrows. Was it coincidence selection bias because we search most carefully near the ecliptic? Or something else? The size estimates were equally intriguing, based on its brightness and assumptions about how reflective its surface might be. Astronomers calculated that 3I Atlas had a diameter somewhere between 5 and 20 kilometers. Even at the lower end of that estimate, this object was massive compared to previous interstellar visitors. Perhaps 1,000,000 times more massive than Oumuamua, about 1,000 times more massive than 2I Borisov. Large interstellar objects should be rarer than small ones. The physics of how planets eject debris from star systems favors smaller chunks. Finding such a substantial visitor so early in our search was unexpected, though not impossible. But the most significant aspect of 3I Atlas wasn't its size or speed or trajectory. It was timing. Orbital calculations showed that this comet would reach perihelion, its closest approach to the Sun, on October 29, 2025, at a distance of 1.36 astronomical units. That's roughly 203 million kilometers just inside the orbit of Mars. Close enough for intense solar heating, close enough to make the comet extremely active, close enough to give us an unprecedented opportunity. You see, Oumuamua had already passed perihelion when we discovered it. We only saw it leaving already cold and quiet. 2I Borisov reached perihelion at 2.0 AU, far enough from the Sun that heating was relatively gentle. But 3I Atlas would experience the most intense solar radiation ever observed on a confirmed interstellar object. For 4 months from July through October, we would watch this visitor approach our Sun, heating up, becoming active, revealing its secrets. We had time to prepare, time to position spacecraft, time to allocate telescope time at observatories around the world, time to coordinate the most comprehensive observation campaign ever directed at an interstellar object. The discovery sparked immediate excitement in the astronomical community. Papers were written, observing proposals were submitted. Amateur astronomers marked their calendars. This was our chance to study material from another star system, to understand the chemistry and physics of a place beyond our cosmic home. Professional astronomers mobilized with remarkable speed. Telescope allocation committees, which normally require months of lead time for scheduling expedited proposals related to 3I Atlas. Graduate students suddenly found their thesis topics. Postdoctoral researchers pivoted their focus. Even senior scientists with established research programs made room in their schedules for this unexpected visitor. The excitement was palpable, but it was also tinged with urgency. Interstellar objects don't linger. They pass through our solar system once and never return. Miss your observing window, and you miss it forever. The pressure to gather data to not waste this opportunity weighed on every astronomer involved. Amateur observers felt this pressure too. Online forums dedicated to comet observation exploded with activity. Observers shared equipment recommendations, optimal viewing times, image processing techniques. A global network of dedicated sky watchers prepared to contribute their observations to the professional dataset. This collaboration between professional and amateur astronomy is one of the field's greatest strengths. Amateurs often have flexibility that professionals lack. They can observe on short notice when something unexpected happens. They can monitor objects continuously when professional facilities can only allocate limited time. They provide geographic coverage that no single observatory can match. For 3i Atlas, this meant truly global surveillance. When darkness fell in Hawaii, observers in Europe were ready. When European skies brightened with dawn, astronomers in Chile took over. The sun never set on the observation campaign, but as observations accumulated through July and into August, something unexpected began to emerge. This comet wasn't behaving quite like we expected. Small anomalies appeared in the data, unusual properties, things that didn't quite fit the standard models. And in those anomalies, in those small divergences from expectation, some people began to see patterns, to wonder if perhaps this visitor from the stars might be more than just a chunk of ice and rock, to ask questions that most scientists considered premature, if not outright absurd. 3i Atlas was coming. The countdown to perihelion had begun, and the world was watching. Before we can understand what made 3i Atlas unusual, we need to understand what normal looks like. What should happen when a comet passes close to the sun? Comets are often called dirty snowballs, and while that's a simplification, it captures the basic idea. The nucleus of a comet is a solid mixture of water, ice, frozen carbon dioxide, frozen carbon monoxide, other volatile compounds, and dust, rocky, and metallic particles mixed throughout. Most comets in our solar system formed in the cold outer regions beyond Neptune's orbit, where these ices could remain stable for billions of years. When a comet ventures into the inner solar system, the sun's warmth changes everything. Solar radiation hits the nucleus, heating the surface. Different ices have different sublimation temperatures, the temperature at which they transition directly from solid to gas without melting. Water ice sublimes at temperatures above about 200 Kelvin, roughly minus 73 degrees Celsius. Carbon dioxide sublimes at much lower temperatures around 150 Kelvin. Carbon monoxide is even more volatile, subliming at temperatures below 70 Kelvin. As the comet approaches the sun and the surface heats up, these ices begin to sublimate. Gas escapes from the nucleus, carrying dust particles with it. This creates the coma, the fuzzy atmosphere of gas and dust surrounding the nucleus that makes comets visible. The coma can extend hundreds of thousands of kilometers from the tiny nucleus. The escaping gas and dust then interact with sunlight and the solar wind. Radiation pressure from sunlight pushes the dust particles away from the sun, creating the dust tail. The solar wind, charged particles streaming away from the sun, sweeps up ionized gas molecules, creating the ion tail. Both tails point generally away from the sun, giving comets their distinctive appearance. For 3i Atlas approaching perihelion at 1.36 AU, we could predict fairly accurately what should happen. At that distance, the solar flux, the amount of solar energy per square meter, is about 770 watts per square meter. To understand what that means, let's do some calculations. If 3i Atlas has a diameter of 10 kilometers, reasonably close to the middle of size, estimates its surface area is roughly 314 square kilometers, or 314 million square meters. Multiply by 770 watts per square meter, and you get about 240 gigawatts of power hitting the comet at perihelion. That's an astonishing amount of energy. For comparison, a large nuclear power plant generates about 1 gigawatt. The total power hitting 3I Atlas at perihelion equals the output of 240 nuclear power plants. But comets don't absorb all that energy. Much of it is reflected back into space. Some is radiated away as infrared. The rest drives the physical processes we observe: sublimation, outgassing, dust ejection. Based on previous observations of comets at similar distances, we expected 3I Atlas to brighten as it approached perihelion. The brightness increase would be gradual, predictable, following well-established models. The coma would expand. The tail would become more prominent. We might see the rotation period change slightly as asymmetric outgassing imparted torque to the nucleus. There was also a possibility, though not a high probability, that the comet would fragment. Thermal stress combined with internal pressure from sublimating ices can sometimes tear a comet apart. About 5% of comets that pass close to the Sun break into pieces. If 3I Atlas fragmented, we'd see it split into multiple objects, each with its own coma following slightly different trajectories. Another possibility was an outburst, a sudden dramatic increase in brightness lasting hours or days. Outbursts occur when a pocket of highly volatile material suddenly vaporizes or when a surface layer collapses, exposing fresh ice beneath. Perhaps one comet in 20 undergoes a major outburst during perihelion. The observatories were ready. Hubble Space Telescope had allocated time for observations. James Webb Space Telescope would point its infrared instruments at the comet, capable of detecting molecules invisible to optical telescopes. Ground-based facilities from Hawaii to Chile prepared observation campaigns. Spacecraft were positioned too. The Solar and Heliospheric Observatory SOHO, with its coronagraphs designed to block the sun's glare, could track objects passing near our star. The Stereo A spacecraft, viewing the sun from a different angle than Earth, provided additional coverage. GOES-19, a weather satellite, would contribute its observations. Mars presented a special opportunity. 3I Atlas would pass within about 29 million kilometers of the red planet on October 3, 2025. Multiple spacecraft orbiting Mars, ESA's Mars Express, ExoMars Trace Gas Orbiter, and NASA's Mars Reconnaissance Orbiter, could potentially observe the comet from a unique vantage point. Amateur astronomers around the world prepared as well. While 3I Atlas would never be bright enough for naked eye visibility, requiring at least an 8-inch telescope to observe, thousands of dedicated observers were ready to contribute data. Amateur observations have historically been crucial for cometary science, often capturing data that professional observatories miss. The expectations were clear. We'd see a comet behaving like a comet. Gradual brightening, predictable outgassing, perhaps some surprises, but nothing that violated known physics. We'd gather unprecedented data about interstellar material, learn about the chemistry of another planetary system, and add one more data point to our understanding of the population of objects drifting between the stars. What we expected was science proceeding normally. Observations leading to measurements, leading to papers, leading to incrementally increased knowledge. What we got was anything but normal. The first hint that 3I Atlas might not be an ordinary comet came in late July, when observers noticed something peculiar about its tail. Comets' tails point away from the sun. That's basic astronomy taught in every introductory class. Solar radiation and the solar wind push material away from the comet, creating tails that stream in the anti-solar direction. Sometimes you can see a slight curve in the tail, and sometimes viewing geometry creates illusions, but the fundamental direction is always away from the star. 3I Atlas had a tail pointing toward the sun. The Nordic Optical Telescope in the Canary Islands captured high-resolution images on multiple nights in late July and early August. The images clearly showed jets of material emanating from the sunward side of the nucleus. This wasn't an optical illusion caused by viewing a curved tail edge-on. Multiple observations from different angles confirmed it. Material was moving toward the sun, or at least appearing to do so. Astronomers call these anti-tails, and they're not completely unknown, but they're rare and usually explainable as geometric effects. The 3I Atlas anti-tail didn't fit the standard explanations. It showed characteristics suggesting genuine sunward motion, driven by active outgassing from the day side of the nucleus. For a few weeks before the full explanation emerged, the anti-tail generated considerable speculation. If material is moving toward the sun, that requires force.
What force could overcome solar radiation pressure and solar wind? Asymmetric outgassing can create jets in various directions, but sustained sunward motion was difficult to explain with conventional models. Some observers, particularly those already inclined toward exotic explanations, suggested the anti-tail might be evidence of propulsion. A spacecraft using directed gas jets for deceleration might produce exactly this appearance. The speculation spread through online forums and social media, amplified by people eager to see something extraordinary. But as more data accumulated, particularly spectroscopic observations, analyzing what gases were being emitted, a natural explanation emerged. The key was carbon dioxide. Most comets in our solar system are water-dominated. Water ice comprises the bulk of their frozen material.
But spectroscopic observations from James Webb Space Telescope revealed something remarkable about 3I Atlas. It had the highest carbon dioxide to water ratio ever observed in a comet. This wasn't just unusual, it was extreme. Solar system comets typically have much more water than CO2, often by factors of 10 or more. 3I Atlas appeared to be the opposite, dominated by carbon dioxide with relatively small amounts of water ice. This composition explained the anti-tail. Carbon dioxide sublimes at much lower temperatures than water ice. When 3I Atlas was still far from the sun at 4 AU and beyond its surface, temperature was too cold for water to sublimate significantly. But CO2 was vaporizing actively. Carbon dioxide sublimation behaves differently than water sublimation. CO2 can build up pressure beneath surface layers, creating pockets of gas that eventually break through in directed jets. The angle and direction of these jets depends on where the CO2 is sublimating most actively and how it's escaping through surface features. For a comet with high CO2 content and particular rotation orientation, you can get jets that appear sunward. They're not really moving toward the sun in the sense of being attracted to it. They're erupting from the day side of the nucleus in directions that happen to have a sunward component. As 3I Atlas continued its approach through August and September, getting closer and warmer water ice began to dominate the outgassing. Water creates more diffuse sublimation patterns, less prone to dramatic jetting. By early October, the anti-tail had disappeared, replaced by normal-looking tail structures pointing away from the sun. The transition from anti-tail to normal tail corresponded exactly with the transition from CO2-dominated to water-dominated outgassing. The mystery was solved through careful spectroscopy and patient observation.
But the anti-tail wasn't the only unusual characteristic. The extremely high CO2 to water ratio itself demanded explanation. Where and how did 3I Atlas form to have such unusual composition? Comets in our solar system formed in the cold outer regions, but even there, water ice is abundant. The molecular cloud that collapsed to form our sun contained significant water. The ratio of elements, hydrogen, oxygen, carbon, favored water formation over CO2 formation. For 3I Atlas to be so CO2-rich suggests it formed in a very different environment, perhaps around a star with different elemental abundances, perhaps in an exceptionally cold molecular cloud where CO2 could condense preferentially. Perhaps in the outer reaches of its parent system, where conditions were unlike anything in our solar system's formation region. This wasn't just unusual. This was our first direct evidence that planetary systems can have fundamentally different chemistry. The building blocks, the raw materials from which planets and comets form, can vary dramatically from one star system to another. Then came the nickel. In August, as 3I Atlas crossed the 3 AU distance from the Sun, spectroscopic observations from the Very Large Telescope in Chile detected atomic nickel vapor in the comet's coma. Nickel emission from comets isn't unprecedented. It's been observed in several solar system comets, and in the previous interstellar visitor 2I Borisov. What was unprecedented was detecting nickel at such a large distance from the Sun. Nickel is a metal with a high vaporization temperature. At 3 AU solar heating should be far too weak to vaporize metal. Yet there it was clearly visible in the spectrum, the characteristic emission lines of atomic nickel. And there was something else. The spectrum showed nickel but very little iron. In natural materials, nickel and iron almost always occur together. They're both siderophile elements. They like to bond with each other. Meteorites contain nickel-iron alloys. When you vaporize metal-bearing rock, you typically see both nickel and iron vapor in similar ratios. 3I Atlas showed strong nickel emission, but barely detectable iron. The nickel-to-iron ratio was completely wrong, orders of magnitude different from what you'd expect. How do you explain nickel vapor without iron vapor appearing at distances too far for ordinary metal vaporization? One hypothesis suggested the nickel might be bound in compounds that vaporize at low temperatures. Perhaps nickel carbonyl NiCO4, an organometallic compound that's volatile at relatively low temperatures. Perhaps nickel sulfides or other complexes that could break apart under sunlight even when the temperature was too low for pure metal vaporization. Another possibility was that cosmic ray bombardment during 3I Atlas's journey through interstellar space had altered its surface chemistry. High-energy particles striking the surface over millions of years could create unusual compounds, preferentially sputter away certain elements, or otherwise modify the composition in ways that create unexpected emission signatures. These were speculations, hypotheses to explain observations that didn't fit standard models. The nickel anomaly remained unexplained, though it was clearly a natural phenomenon. Metals don't spontaneously appear in comet comas. Some process was releasing the nickel, even if we didn't fully understand what that process was. There was also the matter of when 3I Atlas became active. First observations in early July showed a visible coma when the comet was still 4.5 AU from the Sun. Most solar system comets don't develop visible comas until they're inside 3 AU. The early activity suggested that 3I Atlas contained highly volatile materials ices that could sublimate at very low temperatures. This was consistent with the high CO2 content, but the extent of the activity implied a lot of volatile material, more than typical for comets at such large distances. Each anomaly individually could be explained, even if the explanations required some stretching of standard models. The CO2 dominance, while extreme, wasn't impossible. The nickel emissions, while puzzling, had potential explanations. The early activity fit with the volatile rich composition. But taken together, these early observations painted a picture of an object that was pushing at the boundaries of what we expected from comets, not breaking the rules of physics, but definitely not following the usual patterns. And these were just the early anomalies observed when the comet was still far from the Sun. As 3I Atlas continued its approach toward perihelion, more surprises awaited. Dr. Avi Loeb, professor of astronomy at Harvard University and former chair of the astronomy department, developed a rating system specifically for evaluating interstellar objects. The Loeb scale runs from 0 to 10, where 0 means definitively natural and 10 means definitively technological. Most objects, asteroids, comets, space rocks of all descriptions, rate a solid 0. They're natural objects behaving exactly as natural objects should. No ambiguity. Oumuamua, the first confirmed interstellar visitor, was unusual enough to merit discussion.
Its elongated shape, its slight acceleration as it left the solar system, its lack of visible coma. Despite passing near the Sun, these characteristics prompted debate. Some researchers, including Loeb himself, suggested it might rate as high as 5 or 6 on the scale. Most astronomers disagreed, keeping it at 1 or 2 natural but mildly unusual. 3IR Atlas, according to Loeb's assessment, rated a 4, natural but weird.
Ordinary in most respects, but with enough peculiarities to make you look twice. Not evidence of anything artificial, but definitely not typical. Let's examine the 8 specific anomalies that contributed to this rating. These aren't conspiracy theories or speculation. These are documented observations, measurements made by professional instruments, confirmed by multiple independent observers. The question isn't whether these anomalies exist. The question is what they mean. Anomaly 1. Trajectory. Alignment. 3I Atlas entered our solar system on a path that lies within 5 degrees of the ecliptic plane, the flat disk where planets orbit. If interstellar objects arrive from random directions distributed isotropically across the celestial sphere, the probability of any given object aligning this closely with the ecliptic is about 0.2%. Now there's a selection effect here. Survey telescopes like Atlas spend most of their time searching near the ecliptic because that's where most solar system objects are found. If you're looking for asteroids that might threaten Earth, you naturally focus on the ecliptic region. So we might be biased toward discovering interstellar objects in that plane simply because we're looking there most carefully. But 3I Atlas was bright enough and close enough that surveys looking elsewhere probably would have found it too. The alignment is real, even if its significance is debatable. Anomaly 2. The anti-tail evolution. We've discussed the anti-tail already, sunward-pointing jets observed in July and August that transition to normal tail structures as the comet approached the Sun. The natural explanation involving CO2 sublimation is convincing, but the transition itself reveals that 3I Atlas has unusual composition. That CO2 to water ratio isn't just different from solar system comets. It's more extreme than any comet ever observed. It requires formation conditions unlike anything in our planetary system. Anomaly 3. Extreme composition. The James Webb Space Telescope observations in August revealed unprecedented composition. Not just high CO2, but the highest CO2 to water ratio ever measured in any comet. Combined with the nickel without iron signature detected by the Very Large Telescope, we're looking at chemistry that doesn't match our models. This tells us something profound. The parent planetary system where 3I Atlas formed had different chemistry than our solar system. The molecular cloud, the raw materials, the formation conditions, something was fundamentally different. Anomaly 4. Size and mass size estimates place 3I Atlas somewhere between 5 and 20 kilometers in diameter, with best estimates around 10 kilometers. That makes it roughly 1,000,000 times more massive than Oumuamua and about 1,000 times more massive than 2I Borisov. Statistically, larger objects should be rarer. Models of how planetary systems eject debris predict that small chunks should vastly outnumber large ones. Finding such a substantial interstellar visitor this early in our search is unexpected. With only 3 data points, 1 tiny object, 1 medium object, 1 large object, we can't say much about the true size distribution. Maybe our models are wrong. Maybe detection bias favors larger objects more than we realized. Or maybe we've been remarkably lucky or unlucky in what we've found so far. Anomaly 5. Extreme velocity. 3I Atlas is moving at 68 kilometers per second relative to the Sun, and even faster relative to the local standard of rest, the average motion of stars in our galactic neighborhood. This velocity is more than double that of previous interstellar visitors. High velocity means either a long journey or a strong gravitational kick from whatever ejected it. When researchers tried to trace 3I Atlas's path backward through the galaxy, Accounting for gravitational perturbations from nearby stars, the trail went cold after about 10 million years. Beyond that, uncertainties become too large. We know it came from the general direction of Sagittarius toward the galactic center, but there are billions of stars in that direction. Identifying the specific parent system is probably impossible. Anomaly. 6. Timing and planetary encounters. This one is subtle and easily dismissed as coincidence. 3I Atlas's trajectory brings it within tens of millions of kilometers of Mars, Venus, and Jupiter, close encounters with 3 major planets. Meanwhile, it reaches perihelion when it's positioned behind the Sun from Earth's perspective, creating a natural observational blackout. Calculate the probability of this specific configuration close planetary approaches combined with Earth obscuration during the most critical observation period, and you get numbers below 1%, perhaps as low as 0.5%. Is this evidence of design? Almost certainly not, but it is an unusual set of circumstances. If you were planning a reconnaissance mission to study multiple planets while minimizing detection, you'd choose a trajectory very similar to 3I Atlas's actual path. Anomaly. 7. Structural integrity. Many comets that pass close to the Sun fragment under thermal and tidal stress, about 5% split apart. 3I Atlas, subjected to intense heating at perihelion, remained intact. No fragmentation observed. This suggests the nucleus is either structurally stronger than typical comets, denser, smaller than we think, or bound together by something beyond just weak gravitational self-attraction and frozen ices. Anomaly. 8. Long-duration activity. 3I Atlas showed visible coma and active outgassing from 4.5 AU inward, remaining active throughout its approach. Most solar system comets don't become active until inside 3 AU. The early and sustained activity implies large quantities of highly volatile materials. This fits with the CO2-rich composition, but the amount of volatiles implied by the observed activity level exceeds typical expectations. It suggests either the comet is larger than we think or has an unusually high volatile content, even for a CO2-dominated object.
Each of these 8 anomalies has potential natural explanations. Each one individually can be accommodated within our understanding of how comets work, even if it requires pushing at the edges of our models. But compound probability is tricky when you have 8 low probability characteristics all present in the same object. You have to ask, is this just normal variation in a population we don't yet understand well, or is something genuinely unusual happening? With a sample size of 3 interstellar objects, we can't answer that question definitively. We don't know what normal looks like for the interstellar population. Maybe 3I Atlas is perfectly typical for comets from other star systems, and it's our solar system comets that are unusual. Or maybe 3I Atlas is genuinely an outlier, a rare specimen even among interstellar objects. An ancient comet billions of years old, formed under exotic conditions, processed by its long journey through the interstellar medium in ways that no solar system object has experienced. The Loeb scale rating of 4 reflects this ambiguity, not evidence of anything extraordinary but strange enough to warrant careful attention, natural but pushing at the boundaries of what we expected, and all of these anomalies were observed before perihelion. The real test, the moment that would either confirm 3I Atlas as merely unusual or reveal something more surprising, was still approaching. October 29th, the day when this visitor from the stars would swing around our sun at maximum velocity, bathed in maximum radiation, experiencing conditions that would stress every component of its structure. The day when, if anything unusual was going to happen, it would happen. October 21st, 2025. 3I Atlas reached solar conjunction, crossing the imaginary line between Earth and Sun. From our perspective, the comet moved into the Sun's glare, becoming nearly impossible to observe with ground-based telescopes. For the next 3 weeks, we would be essentially blind. We had spacecraft observations, coronagraphs that could block the sun's overwhelming light, but the detailed high-resolution observations that ground-based telescopes provide would be impossible. This created what astronomers call an observational blackout. Not complete darkness, we weren't entirely blind, but severely limited capability, right when we most wanted full visibility. 8 days later, on October 29th, at exactly 11:47 Universal Time, 3I Atlas reached perihelion, closest approach to the sun, the moment of maximum heating, maximum stress, maximum activity. If this comet was going to do something unexpected, this was when it would happen. The physics of perihelion are worth understanding. At 356 astronomical units from the Sun, roughly 203 million kilometers, 3I Atlas was experiencing solar radiation intensity of about 770 watts per square meter. For a 10-kilometer diameter nucleus, that's approximately 240 gigawatts of power hitting the surface. The comet was traveling at 68.3 kilometers per second at perihelion. At that velocity, it was covering the distance from Earth to Moon in less than 2 hours. The momentum was enormous. Any force trying to deflect or alter the trajectory would be fighting against tremendous inertia. This is where the Oberth effect becomes relevant. The Oberth effect is a principle of orbital mechanics that says burning fuel when you're moving fastest gives you the maximum change in kinetic energy for a given fuel expenditure. It's why spacecraft often perform engine burns at periapsis, the point of closest approach, rather than at other points in the orbit. If 3I Atlas carried any kind of propulsion system, if it were going to perform any maneuver, perihelion was the optimal moment. Any course correction, any velocity change would be most efficient here. This is what Dr. Loeb meant when he called perihelion the acid test. If 3I Atlas were artificial, if it were some kind of probe or spacecraft, perihelion would be when it would act. The geometry was perfect. The efficiency was maximum. If something was going to happen that revealed non-natural characteristics, it would happen now. The spacecraft watched. SOHO's LASCO coronagraphs tracked the comet through the solar glare. Stereo A viewing from a different angle maintained observation. GOES 19's solar coronagraph, primarily designed for space weather monitoring, captured images. The Punch satellite quartet coordinated observations. And what did they see? A comet. Just a comet, outgassing, brightening, following Newton's laws, behaving exactly as physics predicted.
No lateral acceleration, no trajectory changes, no anomalous emissions. The speed remained locked at 68.3 kilometers per second. The hyperbolic orbit held. Every measurement, every observation, every data point aligned with natural cometry behavior. But here's where the story becomes genuinely fascinating, because while nothing dramatic happened while 3I Atlas behaved naturally, what did happen was unprecedented in its own right. The comet brightened rapidly, dramatically, far exceeding model predictions. When ground-based observers had last seen 3I Atlas in early October, it was glowing at about magnitude 11.5 faint, requiring large telescopes to observe. Models predicted it would brighten to perhaps magnitude 10 or 9.5 at perihelion, gradual increase following the inverse square law as it got closer to the Sun. The spacecraft observations told a different story. Astronomers Chicheng Jiang from Lowell Observatory and Carl Battams from the U.S. Naval Research Laboratory analyzed the coronagraph data and published their findings in a preprint paper. They reported that 3I Atlas underwent rapid brightening as it approached perihelion, reaching an estimated magnitude of around 9 at closest approach. That might not sound dramatic, but brightness scales are logarithmic. Each magnitude is about 2.5 times brighter than the previous. The difference between magnitude 11.5 and magnitude 9 represents an increase of more than 6 times the expected brightness. The paper's conclusion was stark. The reason for 3I Atlas's rapid brightening, which far exceeds the brightening rate of most Oort cloud comets at similar distances from the Sun, remains unclear. In scientific language, that's as close as you get to saying, "We don't know what's happening." But the brightening anomaly was just the beginning. The color was even stranger. Soho's instruments included not just imaging, but also basic color analysis. The data showed something that shouldn't be possible. 3i Atlas appeared bluer than the sun. Let me explain why that's extraordinary. Comets are cold objects. Even at perihelion, even bathed in intense solar radiation, the surface temperature of a comet's nucleus is far below the sun's 5,800 Kelvin photosphere temperature. Cold objects glow redder than hot objects. That's basic thermal radiation physics. Moreover, comets are dusty. When sunlight reflects off dust particles, it gets scattered and reddened. The same physics that makes Earth's sunsets red applies to cometary dust. Scattered light should be redder than the original sunlight. Think about what this means physically. Dust particles in the comet's coma are tiny micron-sized grains of silicate minerals, organic compounds, perhaps metal particles. When sunlight hits these grains, shorter wavelengths, blue light scatter more strongly than longer wavelengths. Red light. This is Rayleigh scattering, the same phenomenon that makes our sky blue. But in a dusty coma with many particles, multiple scattering events occur. Blue light that scattered once gets scattered again and again, losing energy with each interaction. The net effect is that the light that reaches us has shifted toward the red end of the spectrum. Every comet ever observed follows this pattern. Dusty comets appear reddish-brown or orange. Gas-rich comets might appear greenish from diatomic carbon emission, but never bluer than the sun itself. Until 3i Atlas at perihelion, the color measurements from SOHO and stereo weren't ambiguous. They weren't marginal detections. The comet's light was definitively shifted toward the blue compared to solar light, by several percent, a statistically significant, unmistakable signal. For this to happen, the coma must be dominated by fluorescence rather than reflected light. Gas molecules absorbing ultraviolet photons from the sun and re-emitting visible light. Specifically, diatomic carbon C2 emits strongly around 514 nanometers cyan blue. Cyanogen CN contributes at similar wavelengths. But here's the problem: to make the coma bluer than the sun, you need an extreme gas-to-dust ratio, far more gas than dust, and the gas production rate must be enormous, flooding the coma with so many molecules that their fluorescence overwhelms any scattered sunlight from dust. This requires either a very gas-rich composition or very efficient gas production. CO2-rich comets can achieve high gas production, but the level implied by 3i Atlas's blue color is extreme even for CO2-dominated objects. And there's another puzzle within the puzzle. Different wavelengths of the blue emission correspond to different molecules and different excitation mechanisms. Detailed spectroscopy during perihelion was limited by the observing geometry, but what data exists suggests that multiple molecular species were contributing to the blue color. Not just C2 and CN, but possibly other carbon compounds, maybe even more exotic molecules. The blue color persisted for at least 24 hours around perihelion, based on the spacecraft observations we have. Then, as 3i Atlas moved away from closest approach, as heating decreased, as outgassing rates declined, the color presumably normalized. We'll know for sure when ground-based observations resume in November, but the expectation is that the extreme blue appearance was a transient phenomenon tied specifically to maximum perihelion heating. Transient, yes, but unprecedented, and unexplained beyond the general framework of gas-dominated fluorescence, which is more of a description than an explanation. So a comet at perihelion should appear redder than the sun, definitely not bluer. Yet the observations clearly showed 3i Atlas glowing with a blue-shifted spectrum. The light from the comet's coma was bluer than solar light. The only way this makes sense is if the brightness is dominated not by reflected sunlight or thermal emission, but by fluorescence gas molecules absorbing solar ultraviolet light and re-emitting it at visible wavelengths.
Specifically, diatomic carbon C2 and cyanogen compounds emit strongly in blue-green wavelengths. If 3I Atlas's coma was gas-dominated rather than dust-dominated, if the ratio of gas to dust was much higher than typical, that could produce a blue appearance. But this would imply extraordinary outgassing rates far beyond what you'd expect, even for a volatile-rich comet at this distance. The blue color remained unexplained. Not impossible, but definitely not fitting neatly into standard models. These observations, the rapid brightening, the impossible color, were documented by multiple independent instruments on different spacecraft. This wasn't measurement error. This wasn't artifact. Something genuinely unusual was happening. And yet nothing artificial was detected. No course changes, no signs of propulsion. No electromagnetic emissions that couldn't be explained by natural processes. The trajectory held perfectly to the predicted path. The orbital elements remained consistent with a purely ballistic trajectory governed by gravity alone. Physics 101 was maintained. Newton's laws were unviolated. The comet passed perihelion exactly as predicted, precisely on schedule, following the mathematics of gravity and momentum. For those who had expected something extraordinary, first contact alien revelation, confirmation of technological origin perihelion, was profoundly disappointing. The silence was total. Nothing happened. For those who had expected natural behavior, perihelion was deeply puzzling. The observations showed anomalies that didn't fit models' behavior, that challenged explanations, characteristics that remained unclear. The acid test delivered an ambiguous result. 3I Atlas behaved naturally in the most important ways, its trajectory, its basic physics, but it behaved unnaturally in others, its brightening rate, its color, its energy budget. It was as if the comet was trying to tell us something, showing us properties that don't quite fit our understanding, while simultaneously confirming that it's bound by the same physical laws as everything else in the universe. October 29th came and went. The moment passed. 3I Atlas swung around the sun and began its outbound journey, accelerating away from our star headed back toward the outer solar system and eventually toward interstellar space. But the story was far from over, because perihelion wasn't the end of observations. It was just the most dramatic moment in a much longer campaign. The spacecraft had gathered their data. Soon, ground-based telescopes would regain line of sight as 3IR Atlas moved away from the sun's glare. More observations were scheduled. More spacecraft encounters awaited. And perhaps most intriguingly, some of the data from perihelion wouldn't be available for months. Technical constraints and transmission delays meant we'd be waiting to see the full picture. The silence at perihelion wasn't absence of information. It was deferred information. The universe had shown us something. We just hadn't fully interpreted it yet. Let's ground ourselves in the most scientifically supported explanations. These hypotheses represent mainstream scientific thinking, backed by established physics, and supported by the majority of researchers studying 3I Atlas. The CO2-dominated comet model. The key to understanding most of 3I Atlas's behavior lies in its composition. A comet dominated by carbon dioxide rather than water ice behaves differently than typical solar system comets. This isn't speculation. It's confirmed by spectroscopic observations from James Webb Space Telescope. Carbon dioxide sublimes at lower temperatures than water. At distances where water ice remains frozen, CO2 can be actively vaporizing. This explains the early activity observed at 4.5 AU. This explains the anti-tail formation in July and August CO2-driven jets creating unusual outgassing patterns. As the comet approached and surface temperatures rose, water ice began to sublimate, eventually dominating the outgassing. The transition from CO2-dominated to water-dominated corresponds exactly with the disappearance of the anti-tail and the emergence of normal tail structures. This model is elegant. It explains multiple anomalies with a single underlying cause, unusual composition resulting from formation in a different environment than our solar system's comets. Where did such a comet form? Several possibilities exist. Perhaps around a star with different elemental abundances enriched in carbon relative to oxygen. Perhaps in an exceptionally cold region of a protoplanetary disk where CO2 could condense preferentially. Perhaps in a molecular cloud that had been processed by previous generations of stars, altering its chemistry. The age estimates for 3I Atlas range from 3 to 11 billion years old. Our solar system is 4.6 billion years old. 3I Atlas might predate our sun, formed when the galaxy was younger and had different chemical composition. The nickel mystery. Organic complexes. The nickel emissions without corresponding iron represent a genuine puzzle, but several natural explanations are plausible. Nickel carbonyl NiCO4 is an organometallic compound that's volatile at relatively low temperatures. If nickel in 3I Atlas is bound in such compounds rather than in pure metal or metal alloys, it could vaporize at temperatures too low for iron-bearing minerals to sublimate. Another possibility involves sulfides. Nickel sulfides can have different volatility than iron sulfides. Preferential vaporization of nickel-bearing compounds could create the observed emission signature. A third option considers surface processing. During millions or billions of years, in interstellar space, cosmic rays bombard the surface. High-energy particles can alter chemistry, create new compounds, even preferentially sputter away certain elements. The surface we observe might be quite different from the interior, processed by the harsh environment of interstellar space. These explanations are speculative but grounded in known chemistry. They require no new physics, just specific conditions or compositions that we don't commonly encounter in solar system objects.
Rapid brightening at perihelion. The brightening rate that exceeded models might result from several factors acting together. First, surface layer removal. As a comet approaches the sun, the outer layers heat and sublimate away. If the surface is covered with low volatility material dust, processed organics, that layer can inhibit outgassing until it's removed. Once fresh, volatile rich ice is exposed, outgassing increases dramatically and brightness surges. Second, asymmetric heating. A comet's nucleus isn't uniform. Some regions have more volatiles, others more dust. As the comet rotates and heats, different regions become active at different times. If particularly volatile rich regions become exposed to sunlight near perihelion, brightness can increase more rapidly than simple distance-based models predict. Third, subsurface pressure. Volatiles sublimating beneath the surface can build pressure.
When this pressure releases through fractures through breakthrough of surface layers, the result is enhanced outgassing and brightness increase. Models of cometary activity necessarily make simplifying assumptions. Uniform composition, symmetric heating, steady-state sublimation. Real comets are messy, complex objects. Deviations from simple models are common. The rapid brightening of 3I Atlas might simply reflect that reality. A comet with heterogeneous composition undergoing complex thermal processing, behaving in ways that simplified models don't capture. The blue color anomaly. The blue appearance at perihelion is harder to explain but not impossible. If the gas-to-dust ratio in 3I Atlas's coma was much higher than typical, fluorescence from gas emissions could dominate over scattered sunlight from dust. Diatomic carbon C2 produces strong emission in the blue-green part of the spectrum. Cyanogen CN contributes as well. A CO2-rich comet might naturally have a high gas-to-dust ratio. CO2 sublimates more vigorously than water, potentially ejecting less dust per molecule of gas. If the nucleus is also depleted in dust, more ice-rich than typical comets, the coma could be gas-dominated. The blue color then becomes a natural consequence of composition and outgassing physics. Unusual, definitely. The most extreme gas-to-dust ratio ever observed, probably, but not impossible. Structural integrity. The fact that 3I Atlas didn't fragment at perihelion suggests a robust nucleus. Several factors might contribute. Size matters. Larger objects are held together more strongly by self-gravity. If 3I Atlas is toward the upper end of size, estimates 15 or 20 kilometers, it would be much harder to disrupt than a smaller comet. Composition also matters. A comet with lower volatile content or with volatiles distributed throughout rather than concentrated in pockets experiences less internal pressure.
Less pressure means less stress and less likelihood of fragmentation. The interstellar journey might have strengthened the structure. Temperature cycling over millions of years can cause sintering ice grains fusing together, creating a more coherent structure than freshly formed ice. Or perhaps 3I Atlas is simply denser than typical comets with a higher rock-to-ice ratio. More rock means more structural strength, long-duration activity. Early activity at 4.5 AU and sustained activity throughout approach fits naturally with a CO2-rich composition. CO2 is far more volatile than water, sublimating at much lower temperatures and greater distances from the sun. If 3I Atlas contains large quantities of CO2 and other supervolatiles, like carbon monoxide, the extensive activity becomes expected rather than anomalous. The amount of volatiles required to sustain this activity might seem large, but remember, we don't know the size precisely. If the comet is toward the upper end of estimates, it could contain enormous reserves of frozen gases.
These natural explanations form a coherent picture. An ancient comet from another star system formed under different conditions than our solar system's comets. Composition dominated by carbon dioxide rather than water, processed by billions of years in interstellar space. Unusual but entirely natural. Every anomaly we've observed can be accommodated within this framework. Nothing requires exotic physics. Nothing demands extraordinary explanations. The mainstream scientific consensus is clear. 3I Atlas is a natural object. The anomalies reflect our limited experience with interstellar objects and the genuine diversity of planetary systems. As we observe more interstellar visitors, we'll build better models. We'll understand the range of natural variation. Let's consider what this consensus means in practical terms. Thousands of professional astronomers have examined the data from 3I Atlas. They've run the numbers. They've compared observations with models. They've discussed the findings in conferences and seminars. They've peer-reviewed papers analyzing every aspect of the comet's behavior. The overwhelming majority conclude natural object unusual composition, no evidence of anything beyond standard physics. This consensus isn't groupthink or scientific conservatism stifling creativity. It's the accumulated judgment of experts who have spent their careers studying comets, who understand the physics and chemistry involved, who know what's possible and what's not. When thousands of qualified experts independently examine the same data and reach the same conclusion that carries weight, it doesn't make them infallibly correct. Science has been wrong before, but it does mean that any alternative explanation must meet an extremely high bar of evidence. The natural explanation has been tested against every observation. It has survived every scrutiny. It makes testable predictions about future observations. It's consistent with known physics and chemistry. It requires no new assumptions beyond this comet formed in a different environment. This explanation is supported by approximately 90% of astronomers studying the object. It's the hypothesis that requires the fewest assumptions, invokes the most established physics, and makes the most testable predictions. It's almost certainly correct, but almost certainly is not the same as definitely. Science thrives on the small margins of uncertainty, on the anomalies that don't quite fit on the questions that remain even after the best explanations are offered. And in those margins, in those small spaces where certainty gives way to possibility, other ideas can be explored. Not because they're likely to be true, but because the process of exploring them, of understanding why they're probably wrong, sometimes teaches us things that straightforward explanations miss. So let's explore the edges.
Let's look at the hypotheses that push natural explanations to their limits, that invoke rare phenomena and exotic conditions. Not because they're likely to be true, but because science advances by examining all possibilities, even the unlikely ones. This is speculation, but it's grounded speculation. These hypotheses invoke natural processes that are real, but rare conditions that are possible, but extreme mechanisms that are understood but seldom observed. Interstellar medium processing space between stars isn't empty. It's filled with diffuse gas dust and high-energy particles. An object traveling through interstellar space for millions or billions of years experiences continuous bombardment. Cosmic rays, high-energy protons, and atomic nuclei accelerated to near light speed strike the surface constantly. Each impact transfers enormous energy to a tiny region. Atoms are knocked out of molecules. Chemical bonds are broken and reformed. The surface layer is literally remade by radiation. Over millions of years, this bombardment can alter surface composition significantly. Elements that are easily sputtered away lighter atoms, weakly bound compounds, are preferentially removed. Elements that form stable radiation-damaged structures accumulate. We've never observed this process directly. No solar system object has spent enough time in interstellar space for these effects to dominate. But the physics is well understood. Material processing by cosmic rays definitely happens. Could this explain the nickel without iron signature? Perhaps. If iron is preferentially sputtered, while nickel becomes incorporated into radiation-resistant compounds, the surface could develop unusual element ratios completely unlike the bulk composition. Could it explain other anomalies? Maybe. Surface darkening from radiation damage could affect brightness and color. Structural changes from billions of years of bombardment might increase cohesion, explaining why the comet didn't fragment. This hypothesis is testable in principle. Future missions to interstellar objects could sample surface material, analyze its structure, look for signatures of long-duration cosmic ray processing. Formation in an exotic environment. Our solar system formed from a specific molecular cloud with specific composition at a specific time in galactic history. That's just one data point in a vast parameter space. Stars form with different elemental abundances. Some are carbon-rich, others oxygen-rich. Some formed from material processed through multiple previous stellar generations, enriched in heavy elements. Others formed from more pristine material. The temperature structure of protoplanetary disks varies. Some stars are hotter, creating larger warm zones. Others are cooler, allowing ices to condense closer in. The disk mass, the presence of nearby stars, the radiation environment, all these factors vary. 3I Atlas might have formed in conditions radically different from anything in our solar system, perhaps around an asymptotic giant branch star, which produces copious carbon. Perhaps in the outer regions of a massive protoplanetary disk where CO2 is the dominant ice. Perhaps in a binary star system where gravitational interactions create unusual disk dynamics. The age estimate of 3 to 11 billion years is significant. If 3I Atlas is at the upper end 11 billion years old, it formed when the galaxy was less than 3 billion years old. The metallicity. The elemental composition of the universe at that epoch was different than today. Fewer heavy elements, different ratios. An ancient object formed in the early galaxy might naturally have composition unlike anything formed more recently. This hypothesis explains the composition anomalies elegantly. It predicts we should see substantial variation in interstellar objects as we observe more of them. Different parent systems, different formation epochs, different chemistry. Internal heat sources. Most heat in a comet comes from the sun, but other heat sources exist. Long-lived radioactive isotopes, uranium-238, thorium-232, potassium-40 decay over billions of years, releasing heat. In a small body, this heat is negligible.
but in a larger body or one with unusual composition enriched in radioactive elements, internal heating could be significant. Residual formation heat is another possibility. When a comet formed, gravitational energy was converted to heat. In most objects, this heat radiated away billions of years ago. But in a large insulating object with low thermal conductivity, heat could be retained for extreme durations. Internal heat sources would allow activity at large distances from the sun. Subsurface ices could sublimate from below even when surface temperatures are far too cold for normal outgassing. This could explain the early activity at 4.5 AU. This hypothesis is harder to test directly, but we might see indirect evidence. Unusual infrared emission patterns. Outgassing that doesn't correlate perfectly with solar distance. Activity that continues long after the comet has moved far from the sun. Electrical and plasma phenomena. Comets move through the solar wind, the stream of charged particles flowing away from the sun. They also have their own extended atmosphere of ionized gas. This creates an electrical environment that's complex and not fully understood. In some circumstances, electrical effects can be significant. Charging of dust grains affects how they move. Plasma instabilities can create unusual emission patterns. Interaction between the comet's magnetic field, if it has one, and the interplanetary magnetic field can transfer energy.
Most of the time, these electrical effects are subtle, secondary to the dominant processes of sublimation and solar radiation. But in unusual circumstances, particular compositions, particular solar wind conditions, they might become more important. Could electrical phenomena explain some of 3I Atlas's behavior? Possibly. The blue color might involve plasma emission rather than just fluorescence. The brightening might be enhanced by electrical discharge processes. This is speculative territory. The physics is real. Plasma effects definitely exist in cometary environments, but whether they're significant for 3I Atlas specifically is uncertain.
These exotic hypotheses stretch our understanding, but don't break it. They invoke real phenomena: cosmic ray processing formation, environment, diversity, internal heating, plasma physics applied in extreme or unusual circumstances. They're less likely than the straightforward natural explanations. They require more specific conditions, more fine-tuning of parameters. But they're not impossible. And they serve a purpose beyond explaining 3I Atlas specifically. They remind us that the universe contains phenomena we rarely see, conditions we haven't studied carefully, processes that operate at extremes we don't encounter in our local environment. As we observe more interstellar objects, we'll test these hypotheses. We'll see if cosmic ray processing is detectable. We'll check if composition variations correlate with estimated age. We'll look for internal heat signatures and plasma effects. Science advances not just by explaining what we observe, but by predicting what we might observe in the future. These hypotheses generate predictions. They can be tested. But there's one more hypothesis we need to address, the one that generated the most attention, the most controversy, the most vigorous debate. The hypothesis that 3I Atlas might not be entirely natural. We need to be absolutely clear about something before going further. What follows is highly speculative. The vast majority of astronomers consider the artificial origin hypothesis for 3I Atlas to be extremely unlikely, perhaps absurdly so. The evidence overwhelmingly favors natural explanations. But the hypothesis was raised by credible scientists. It generated serious discussion, and examining it carefully, understanding why it was proposed and why it's almost certainly wrong, teaches us something valuable about how we think about extraterrestrial intelligence. Dr. Avi Loeb, professor of astronomy at Harvard, assigned a 30 to 40% probability that 3I Atlas might have artificial origins. Not certainty, not even majority confidence, but substantial enough to warrant investigation. His reasoning was based on compound probability. Take all 8 anomalies we've discussed, assign each a probability of occurring naturally. Multiply those probabilities together. The result, he argued, suggested a non-trivial chance that all these features occurring together might indicate something other than pure chance. The counterargument, and it's compelling, is that those probability calculations are subjective and potentially flawed. We don't know the true distribution of interstellar object properties. We can't assign accurate probabilities to characteristics we've barely begun to observe. With a sample size of 3, statistical arguments are nearly meaningless. But let's examine the hypothesis on its own terms. If 3I Atlas were artificial, a probe or spacecraft from another civilization, what would we expect to see? The Oberth maneuver opportunity. In orbital mechanics, the Oberth effect states that a given change in velocity requires minimum energy when performed at maximum velocity. For any spacecraft or probe traveling through a solar system, the optimal time for trajectory corrections is at perihelion, closest approach, highest velocity. If 3I Atlas were artificial and intended to alter its trajectory, perihelion on October 29th was the moment to do it. Any propulsion system, any course correction would be most efficient there. We observed no trajectory changes. The orbit remained perfectly ballistic, governed entirely by gravity. This is strong evidence against artificial origin. But advocates of the artificial hypothesis point out that absence of obvious maneuvering doesn't definitively rule out artificiality. Perhaps the object isn't planning to stay.
Perhaps its mission is reconnaissance, fly through, gather data, leave. No need to maneuver if you're just observing. Or perhaps any propulsion is so subtle, so efficient, that we couldn't detect it against the background of outgassing forces and measurement uncertainties. Tiny trajectory changes too small to measure reliably could still be significant over interstellar distances. This line of reasoning demonstrates the problem with the artificial hypothesis. It's unfalsifiable. Any observation can be explained away. Maneuvering would prove artificiality. Absence of maneuvering is also consistent with artificiality. The hypothesis adapts to fit whatever we observe. Solar energy harvesting. At perihelion, 3I Atlas received approximately 240 gigawatts of solar power. For comparison, that's about the total generating capacity of a medium-sized country. For an advanced civilization sending probes on interstellar missions, power is a fundamental challenge.
Solar panels work near stars but are useless in deep interstellar space. Nuclear power sources are limited by fuel mass. Exotic technologies might exist but are beyond our understanding. A logical solution: design your probe's trajectory to pass close to stars, then harvest solar energy during those encounters. Store it in batteries, capacitors, or some technology we haven't invented. Use that power for propulsion, communications, data processing, whatever the mission requires. This concept isn't science fiction, it's practical engineering, assuming you have the technology for efficient energy storage and very long mission durations. Could 3I Atlas be harvesting solar energy? In principle, yes. Would we detect it? Maybe not. If the energy collection is efficient and the storage mechanism is internal, the only signature might be heat emission. But comets naturally emit heat from sublimation and solar absorption. Distinguishing artificial energy collection from natural thermal processes would be extremely difficult. The rapid brightening at perihelion could, in this framework, be interpreted as energy collection ramping up. The blue color could be something related to power systems. The speculation becomes increasingly strained. The fundamental problem is that every observation consistent with energy harvesting is also consistent with natural processes. Natural explanations are simpler, require fewer assumptions, and don't invoke unproven technology. The camouflage hypothesis. If you were sending a probe to another star system for reconnaissance, how would you design it? One approach: make it obviously artificial. Geometric shape, metallic surface, clear signals, announce your presence. This works if you want to be detected. Another approach: camouflage. Make your probe look like a natural object. coat it in ice and dust, let it accumulate material during its interstellar journey. Match the signature of a comet or asteroid as closely as possible. Observe without being observed. Why would you do this? Perhaps to avoid influencing the civilization you're studying. Perhaps because you don't know if they're hostile. Perhaps because covert observation is simply prudent. Under this hypothesis, 3IO Atlas could be artificial beneath its natural-appearing exterior. The ice and dust are real, accumulated over millions of years, or deliberately applied. The outgassing is real, either from accumulated material or designed to mimic natural behavior. Everything we observe is genuine, but beneath it lies a core of technology. This hypothesis is nearly impossible to disprove without direct sampling. You can't distinguish an artificial probe covered in natural material from a natural object just by remote observation. The two would look identical, but that's also the hypothesis's fatal flaw. It's unfalsifiable. It explains nothing that natural explanations don't explain more simply. It requires extraordinary technology for which we have no evidence. It's invoking invisible pink unicorns. You can't prove they don't exist, but that doesn't make believing in them reasonable. The timing, coincidences. The trajectory of 3I Atlas brings it past Mars near Venus within observational range of Jupiter. Meanwhile, Earth's view is blocked during perihelion. The orbit aligns with the ecliptic where planets reside. Calculate the probability of this exact configuration and you get small numbers. Less than 1%, perhaps much less. Is this evidence of design, of deliberate trajectory, planning by whoever launched this object? No. And here's why. Every specific trajectory is improbable. If 3I Atlas had a different path, say perpendicular to the ecliptic passing above the solar system, we could calculate the probability of that specific trajectory and also find it's unlikely. The fact that any particular outcome is improbable doesn't make that outcome evidence of design. This is the Texas sharpshooter fallacy: fire bullets randomly at a barn, then paint targets around wherever the bullets landed. Look, you hit the bullseye every time. But the pattern was created after the fact by choosing what to measure. We're doing the same thing with 3I Atlas. It has some specific trajectory. We can find things about that trajectory that seem meaningful: planetary encounters, ecliptic alignment, timing of perihelion. But if it had a different trajectory, we'd find different meaningful seeming patterns. Pattern seeking is hardwired into human cognition. We see faces in clouds, hear messages in noise, find significance in coincidence. It's a survival adaptation that occasionally misfires, making us see design where only chance exists. So why did Avi Loeb publicly champion the artificial hypothesis despite these serious objections? His argument is philosophical as much as scientific. We've never confirmed extraterrestrial technology. We don't know what it looks like. Our intuitions about what's obviously natural versus possibly artificial might be completely wrong. An advanced civilization's technology might be so sophisticated that it's indistinguishable from natural phenomena. We might need to examine objects with extreme care, take seriously even very low probability hypotheses, because the consequences of missing actual extraterrestrial intelligence would be enormous. Better, Loeb argues, to look foolish by suggesting artificial origins and being wrong than to miss artificial origins by refusing to look. This position has merit as philosophy. Science should be open-minded. We should consider unusual hypotheses. We shouldn't dismiss ideas just because they make us uncomfortable. But there's a line between open-mindedness and credulity, between considering all possibilities and giving unequal weight to unlikely ones, between intellectual courage and attention-seeking contrarianism. Most astronomers believe Loeb crossed that line with 3I Atlas. The 40% probability he assigned to artificial origins is, in their view, unjustifiably high. The evidence doesn't support it. The publicity it generated was counterproductive, spreading misinformation and conspiracy theories. Loeb's response is that history is full of scientists who dismissed important ideas as impossible. Continental drift, meteorites, the Big Bang. Sometimes the contrarian turns out to be right. True, but more often the contrarian is simply wrong. Most scientific consensus exists for good reasons. When the evidence overwhelmingly points one direction, betting against it requires extraordinary justification. The perihelion passage on October 29th was in Loeb's Framing the Acid Test. If 3I Atlas were artificial, it would reveal itself during that critical moment. It didn't. No maneuvering, no anomalous signals, no deployment of secondary craft, nothing that couldn't be explained naturally. Does this definitively rule out artificial origins? No, and sufficiently advanced and subtle probe could remain undetected even under close scrutiny, but it substantially lowers the probability. After perihelion, even Loeb acknowledged that 3I Atlas most likely is a natural object. The artificial hypothesis, never strongly supported, became even less likely, but the conversation generated by the hypothesis had value. It made millions of people think about how we'd recognize extraterrestrial intelligence. It highlighted the limitations of our detection methods. It forced scientists to articulate clearly why they believe 3I Atlas is natural, a useful exercise even when the conclusion seems obvious. The debate also revealed something about how science communicates with the public. When a prominent scientist publicly assigns a 40% probability to artificial origins, media coverage amplifies that to Harvard professor says alien probe likely. The nuance disappears. The careful qualifications vanish. The message becomes distorted. This isn't just media sensationalism. It's an inherent difficulty in communicating uncertainty. The public wants definitive answers. Is it aliens or not? Science offers probabilities and confidence intervals. Probably not, but we can't rule it out completely. These messages don't translate well across the boundary between scientific discourse and public consumption. Loeb's approach, publicly entertaining the artificial hypothesis, can be seen as either courageously open-minded or recklessly irresponsible, depending on your perspective.
His defenders argue that science advances by considering all possibilities, that ruling things out without investigation is dogmatic. His critics argue that giving unwarranted credibility to unlikely hypotheses spreads misinformation and damages public trust in science. Both positions have merit. The tension between them reflects a deeper question about science's role in society. Should scientists only communicate when they're certain, or should they share their thinking process, including unlikely possibilities, even when that creates opportunities for misunderstanding? There's no easy answer. What's clear is that the 3I Atlas episode will become a case study in science communication. What worked? What failed? How can we do better next time, because there will be a next time? More interstellar objects are coming. Some will be more unusual than 3I Atlas. The questions about artificiality will arise again.
And we need to be better prepared, not just scientifically, but communicatively, to handle those questions when they come. The artificial origin hypothesis for 3I Atlas is almost certainly wrong, but exploring why it's wrong, examining the reasoning behind it, understanding the evidence that refutes it, that's worthwhile. Because someday, perhaps, an object will pass through our solar system that genuinely is artificial. When that day comes, we'll need to recognize it. We'll need to distinguish the truly extraordinary from the merely unusual. 3I Atlas taught us something about that distinction, about the difference between patterns and coincidences, about when anomalies require exotic explanations and when they're just natural variation we haven't seen before. It taught us that the universe is strange enough, diverse enough, surprising enough without needing to invoke aliens. But it also taught us that we can't know for certain without looking carefully. That dismissing possibilities without investigation is as unscientific as believing them without evidence. The lesson is balance. openness to possibility combined with rigor in evaluation. Willingness to consider the extraordinary paired with insistence on extraordinary evidence. That's the legacy of the artificial hypothesis debate, not whether 3i Atlas was alien, but how we approach such questions in general. And that's a lesson worth learning, because the questions will keep coming as we observe more of the cosmos beyond our small planetary home. There's something deeply uncomfortable about timing, about coincidences that seem too perfect, about circumstances that create exactly the conditions conspiracy theories require to flourish. On October 21, 2025, 3i Atlas reached solar conjunction. From Earth's perspective, the comet moved directly between us and the Sun, or more precisely into a position where the Sun's overwhelming glare made ground-based observation nearly impossible. For the next 3 weeks, through perihelion and beyond, we would have limited visibility. Not complete blindness spacecraft with coronagraphs could still observe, but the detailed spectroscopy, high-resolution imaging, and comprehensive monitoring that ground-based telescopes provide would be impossible. The most critical moment in 3i Atlas's passage through our solar system happened when we could barely watch. Let's be clear about the geometry. When an object is within about 10 to 15 degrees of the Sun in our sky, pointing a telescope at it risks damaging instruments. Even if you don't point directly at the Sun, scattered light overwhelms faint objects nearby. The sky becomes a glowing fog. Professional observatories have strict rules about solar elongation. Most won't observe anything within 30 degrees of the Sun. Some push it to 20 degrees in special circumstances with extreme precautions. But closer than that, you're essentially blind. Amateur astronomers can be more daring. They're risking their own equipment, not expensive professional instruments. Some managed marginal observations of 3i Atlas at low solar elongation, using careful techniques to block the Sun's light. But these observations were difficult, uncertain, and limited. For 3 weeks, the object that had captivated global attention was hidden behind our own star, and that timing, that geometrical coincidence, fed every conspiracy theory imaginable. Think about it from the perspective of someone predisposed to see patterns and suspect hidden agendas. An interstellar object, possibly artificial, according to a Harvard professor, arrives in our solar system. It approaches the Sun along a trajectory that brings it past multiple planets. And at the exact moment when it's closest to the Sun, when any propulsion system would be most efficient, when any activity would be most intense, we can't watch. It's like a magician directing your attention elsewhere during the crucial sleight of hand. Look over here at the ecliptic alignment. Look at the unusual composition. Look at the anomalies that make you curious. And then when the real trick happens, when the probe does whatever it's programmed to do, solar conjunction blocks your view. The probability calculations make it worse. What are the odds that an interstellar object would reach perihelion during solar conjunction? As seen from Earth, the calculation isn't straightforward because it depends on the specific orbit, but roughly speaking, about 5 to 10% of possible perihelion times would occur during conjunction. Not astronomically unlikely, not suspiciously impossible, but low enough that you could argue it's convenient if you wanted observations blocked. This reasoning suffers from fundamental flaws, but they're not obvious to non-astronomers. Let's break them down. First, solar conjunction only affects observation from Earth. Spacecraft located elsewhere. Mars' orbit elsewhere in the solar system had different viewing angles. Stereo A, positioned ahead of Earth in our orbit, saw 3i Atlas from a completely different perspective. We weren't entirely blind, just constrained. Second, solar conjunction is common. Objects in the inner solar system regularly pass through conjunction. Every planet does it. Most asteroids do it. If you observe enough objects, many will experience conjunction during whatever specific period you're interested in. It's not rare. Third, even during conjunction, coronagraphs could observe. Soho Stereo Goes 19. Punch all tracked 3i Atlas through perihelion. The observations weren't as detailed as we'd like, but they existed. the blackout wasn't complete. Fourth, if you were designing a reconnaissance mission and wanted to avoid detection, solar conjunction from Earth's perspective is actually a poor choice. Sure, ground-based telescopes can't watch, but you're bathed in intense solar radiation. Your outgassing is at maximum. You're at your brightest and most active. You stand out against the solar background. If you wanted stealth, you'd avoid perihelion altogether, staying in the cold outer system where activity is minimal. But these logical counter-arguments didn't stop the conspiracy theories. Online forums exploded with speculation. YouTube videos with millions of views claimed the conjunction timing proved 3i Atlas was artificial, that governments had arranged the observation blackout, that something momentous would happen during those hidden weeks. The psychology here is fascinating. When humans can't observe something, when we're forced to wait, when information is delayed or incomplete, our imaginations fill the gap.
An imagination unconstrained by data can go anywhere. The waiting period from October 21st through November 11th, when 3i Atlas would emerge from solar glare and become visible to ground-based telescopes, again became a kind of collective holding of breath. What would we see when visibility returned? Would the comet have changed? Would it show signs of having done something during conjunction? Would new anomalies appear? This anticipation, this enforced ignorance, this gap between expectation and observation, it's actually a recurring theme in the history of astronomy. When Mars passes behind the Sun as seen from Earth, we lose contact with Mars rovers for days or weeks. During those blackout periods, conspiracy theorists imagine all sorts of activities happening out of view. Secret missions, hidden discoveries, cover-ups. When the far side of the moon was unexplored, people imagined alien bases there hidden from Earth's view. The first images from Soviet probes disappointed them, just more craters. The gaps in our observation, the limits of our coverage, the blank spaces on the map, these have always been where speculation grows wildest. 3i Atlas's solar conjunction was this generation's version of that phenomenon. A high-profile object, a moment of genuine scientific interest occurring when we couldn't watch directly. And here's the uncomfortable truth that conspiracy theorists seize upon. They're right that we can't watch everything. We don't have comprehensive coverage of the solar system. Objects can do things we don't observe. Small asteroids pass between Earth and Moon, sometimes with only hours of warning. Comets occasionally surprise us. Even with improving technology, space is vast and our surveillance is limited. If an advanced civilization wanted to operate in our solar system covertly, they probably could. Not because of convenient conjunctions, but simply because space is big and our instruments are limited. We notice bright, close objects. We might miss dim, distant ones or objects using stealth technologies we haven't imagined. That's not evidence for aliens. It's just acknowledgement of reality. Our knowledge has boundaries. The solar conjunction of 3i Atlas reminded us of those boundaries. For 3 weeks, we had to trust spacecraft observations, trust the data we could gather, and accept that some details were beyond our reach. And then November 11th arrived. The comet emerged from behind the Sun. Ground-based telescopes locked on. High-resolution observations resumed. What did we see? A comet. Still outgassing, still following its predicted trajectory, still looking like what it appeared to be before conjunction. No dramatic changes. No evidence that anything unusual occurred during the blackout period. The emergence from conjunction didn't end. All speculation conspiracy theories are remarkably resilient, but it did deflate much of the anticipation. The hidden observation window taught us something about ourselves, about how we handle uncertainty, about how gaps in information breed speculation, about how our need for explanation can sometimes overwhelm our patience for evidence. 3i Atlas didn't do anything mysterious during solar conjunction. It just did what comets do, following physics subject to gravity and thermodynamics and all the natural laws that govern motion and matter. The perfect blind spot turned out to be perfectly normal. The timing that seemed too convenient was just timing.
The coincidence was just coincidence, but for those 3 weeks, while we waited and wondered, the universe gave us a reminder we can't observe everything. We have to accept that sometimes things happen outside our view. And perhaps that uncertainty, that incomplete knowledge, that reminder of our limitations, perhaps that's not a bug but a feature. Perhaps not knowing everything, being surprised, sometimes being reminded that the cosmos doesn't organize itself for our convenience. Perhaps that's what keeps us looking up. On October 26, 2025, physicist Dr. Brian Cox posted a warning on social media. He thanked YouTube for removing AI-generated deepfake videos that falsely portrayed him endorsing conspiracy theories about 3I Atlas. Videos showing him calling the object an alien spaceship. Videos claiming NASA was covering up the truth. Videos suggesting humanity should prepare for first contact. None of it real, all of it convincing. Cox added, "Doesn't matter so much if it's nonsense about a comet, but in other areas of science, and certainly politics, it's clearly important." His warning highlighted a problem that went far beyond 3I Atlas. In the months leading up to perihelion, as public interest peaked, the object became a testing ground for misinformation warfare. Deepfakes, fabricated documents, synthetic media, all weaponized to generate confusion, spread conspiracy theories, and undermine scientific authority. It worked terrifyingly well. Let's understand what happened and why it matters for more than just astronomy. The deepfake technology, modern AI, can generate convincing fake videos. Feed it footage of someone speaking, provide a script, and algorithms can make them appear to say anything. The mouth movements sync with the new audio. The lighting matches. The video quality is preserved. For someone scrolling through social media, these fakes are indistinguishable from legitimate content. No obvious tells. No glitches that scream fake. Just apparently real footage of scientists making extraordinary claims. Dr. Michio Kaku was a frequent target. Viral videos showed him stating that 3I Atlas was confirmed as alien technology, that it was harvesting solar energy, that NASA insiders were panicking. The videos accumulated millions of views before platforms removed them. But removal came too late. Once content achieves viral spread, it cannot be contained. People download it, re-upload to other platforms, share via messaging apps. The deepfakes migrated from YouTube to TikTok to conspiracy-focused websites where moderation is minimal. The fabricated emergency. The most damaging deepfake was a supposed emergency press conference. The video showed multiple scientists' faces, synthesized voices generated announcing that 3I Atlas had exhibited clear signs of intelligent control. Trajectory corrections had been observed, they claimed. Radio transmissions detected. Governments were coordinating response protocols. None of it happened. The press conference never occurred. But the video was professionally produced with realistic graphics and data visualizations. Fact-checking organizations had to issue specific debunking articles, which of course the believers dismissed as part of the cover-up. What made this particular fake insidious was how it mixed truth with fabrication. It started with accurate information. 3I Atlas is an interstellar object. It approached perihelion. Some scientists discussed unusual properties. All true. Then it transitioned to fiction. And that transition was smooth enough that viewers didn't notice where reality ended. The NASA shutdown weaponized. The U.S. government shutdown from October 1st through mid-October created a genuine information vacuum. NASA's public communications went silent. While observations continued, the flow of official updates slowed dramatically. Conspiracy theorists seized on this. The timing was too perfect, they claimed. An interstellar object approaches, and suddenly NASA goes dark. Obviously, this was orchestrated to control information flow. The reality government shutdowns resulting from congressional budget failures was too mundane. The conspiracy version was more exciting, more meaningful, more satisfying psychologically. Fabricated NASA memos circulated online. Leaked documents with official-looking letterheads, proper formatting, realistic technical language. One supposed memo from the European Space Agency claimed anomalous electromagnetic readings from 3I Atlas, consistent with active electronics. Completely fabricated, no such memo existed. But it circulated for weeks before official debunking, and even after ESA explicitly stated it was fake, people continued citing it as evidence. The Chinese silenced China's Tianwen-1 Mars orbiter was positioned to potentially observe 3I Atlas during its close pass by Mars on October 3rd. No images were released publicly.
This absence became fuel for speculation. China must have photographed something significant, the theories went. Something that contradicted the official natural comet story. Something revealing artificial structures. Rather than release these controversial images, China stayed silent. The absence of images was in conspiracy logic more significant than any image could be. The reality was simpler and more boring. Tianwen-1's cameras are optimized for photographing Mars from orbit, not distant comets. The observation would have been technically challenging and potentially not worth the effort of retargeting instruments. Even if images existed, China's space program releases data on its own schedule, often months after acquisition. But rational explanations couldn't compete with the exciting conspiracy version. Claims of insider sources within the China National Space Administration circulated, though no such sources ever materialized with verifiable credentials.
The asymmetric battle. Here's the fundamental problem: creating convincing misinformation takes effort, but not as much effort as creating real scientific content. And debunking requires even more effort than creating the misinformation. You can generate a deep fake video in hours. You can fabricate a document in minutes. You can make an extraordinary claim in a single sentence. Debunking requires explaining why it's fake, providing evidence, reaching the same audience that saw the original. It's exhausting, often ineffective, and it's fighting against psychological forces, confirmation bias, desire for exciting explanations, distrust of authority that favor misinformation. Some astronomers took on the role of active debunkers, posting detailed explanations of why specific claims were false. These efforts helped, but they couldn't keep pace. For every false claim debunked, 3 more appeared. Why this matters beyond 3I Atlas. Brian Cox's warning was prescient. If the misinformation techniques developed around 3I Atlas, a relatively low-stakes story about a comet, are applied to higher-stakes situations, the consequences could be severe. Elections, public health crises, international conflicts. Any situation where accurate information matters, where scientific credibility is important, where public trust in institutions is necessary. The infrastructure for creating and spreading convincing lies now exists. It's been tested, it works, and it's getting better. AI-generated content becomes more sophisticated every month. Scientists are grappling with how to respond. Some argue for aggressive public engagement fighting misinformation directly. Others believe that engaging with conspiracy theories legitimizes them, that focus should remain on communicating with people who are genuinely curious. There's no consensus. What's clear is that the old model, publish papers, talk to journalists occasionally, is insufficient. In an environment where anyone can be made to appear saying anything, where fabricated documents look authentic, where misinformation spreads faster than correction, scientists need to be active participants in the information ecosystem, but that's asking a lot. Scientists are trained for research, not for being social media managers. They're already working long hours. Asking them to also police the internet for fake versions of themselves, constantly debunk misinformation, maintain active public presence. It's an additional burden many aren't prepared for. The grifters. Some people spreading misinformation about 3I Atlas weren't believers. They were entrepreneurs who saw an opportunity for profit. Sensational content gets clicks. Clicks generate ad revenue. A video titled 3i Atlas Confirmed as Alien Mothership gets more views than Interstellar Comet shows, unusual but probably natural properties. These grifters created networks of accounts amplifying each other, used search optimization to rank highly, packaged misinformation with enough factual content to seem credible, and monetized aggressively. For them, 3i Atlas wasn't a scientific phenomenon to understand. It was a product to exploit. As 3i Atlas continues its journey away from the sun, the deep fakes and misinformation will fade. The grifters will move to the next viral topic. The conspiracy theories will lose energy, but the infrastructure remains. The techniques are proven. The audience is primed. Next time there's a mysterious object, a confusing scientific finding, anything generating public interest, this playbook will return. Probably more effective than before. The real story of the misinformation around 3i Atlas isn't that people fell for fake videos about a comet. It's that we're now living in an information environment where truth is optional and convincing lies are cheap. The scientists fought back with limited success. The platforms made token efforts, and the misinformation kept spreading because that's what it's optimized to do. We learned something important from this: scientific truth alone isn't sufficient in the modern information landscape. You need truth plus effective communication plus media literacy plus platform cooperation plus the requirements keep growing, and we're still figuring out how to meet them. 3i Atlas. The comet is natural. 3i Atlas. The information phenomenon revealed something troubling about how we share and process information in the 21st century, and that lesson matters more ultimately than anything about the comet itself. Perihelion was never meant to be the end of the story. It was intermission. Because while October 29th gave us one critical data point about what 3i Atlas isn't, it isn't obviously artificial, it isn't maneuvering, it isn't signaling the coming months will tell us what it actually is. And the observation schedule already locked in represents an unprecedented opportunity to study an interstellar object across multiple wavelengths from multiple vantage points, with coordination between professional observatories and spacecraft that has never been achieved before. November 11th, emergence from glare. On this date, about 2 weeks after perihelion 3i Atlas reached sufficient angular separation from the Sun that ground-based telescopes could observe it again without overwhelming solar glare. Amateur astronomers worldwide prepared. The comet would appear in the constellation Virgo low on the eastern horizon before sunrise, magnitude around 11 to 12 faint, requiring telescopes of at least 8 inches aperture. But for dedicated observers, the challenge was worth it. This would be our first clear look at 3i Atlas after perihelion. Had it fragmented, changed brightness unexpectedly, developed new tail structures, professional observatories allocated time as well. The Gemini South Telescope in Chile, the Very Large Telescope, multiple facilities in Hawaii, all turning instruments toward this visitor from beyond. The key questions for these initial post-perihelion observations: what's the rotation period? Asymmetric outgassing can change how an object spins. What's the coma structure? Jets spirals. Asymmetries reveal active regions on the nucleus. What's the dust-to-gas ratio? High ratios mean dust, rich, low ratios gas-rich. Any signs of fragmentation? Even small pieces breaking off would be significant. And critically, continued spectroscopy. What molecules are being emitted now that the comet is moving away from maximum heating? How does the composition change as different ices sublimate at different rates? November 4th. JUICE. Flyby, 5 days before ground-based visibility returns. Something remarkable happens in deep space. The European Space Agency's Jupiter Icy Moons Explorer JUICE spacecraft passes within 64 million kilometers of 3i Atlas. In astronomical terms, that's intimate proximity. JUICE wasn't designed to study comets. It's on its way to Jupiter, where it will spend years examining Europa Ganymede and Callisto icy moons that might harbor subsurface oceans. But mission planners noticed their trajectory would bring them close to 3I Atlas right after perihelion, and they seized the opportunity. JUICE carries impressive instruments: the Janus Visible Light Imager, the MAGIS Infrared Spectrometer, the SWI Sub-Millimeter Wave Instrument, and crucially, magnetometers that can detect magnetic fields. If 3I Atlas has unusual electromagnetic properties, anything that might hint at artificial power systems or active electronics, JUICE is positioned to detect them. But there's a catch, a significant one. JUICE is currently using its main high-gain antenna as a heat shield. The spacecraft is close enough to the sun that it needs protection, and the big dish antenna is perfect for blocking solar radiation. But that means JUICE can only transmit data back to Earth using its smaller medium-gain antenna, and the data rate is painfully slow. The observations will be made in early November. The full data set won't be transmitted back to Earth until February 2026. 4 months of waiting, 4 months of knowing that observations exist but not seeing them. 4 months during which we'll wonder what JUICE saw, what it measured, whether there are surprises in the data. It's agonizing for researchers. It's perfect for building anticipation. December 19th. Closest Earth approach. This is the big one, the date every astronomer studying 3I Atlas has marked. On December 19, 2025, the comet reaches its closest approach to Earth. 1.8 astronomical units, about 270 million kilometers, still distant, nowhere near, collision course, no danger whatsoever, but close enough for excellent observations. Every major telescope on Earth will point at 3I Atlas. Hubble Space. Telescope observations are scheduled. James Webb Space Telescope will turn its infrared instruments toward the comet. Ground-based facilities from Hawaii to Chile have allocated prime observing time. This is when we'll get the highest quality data, when we'll resolve details impossible to see at greater distances, when spectroscopy will reveal the most complete picture of composition. Several specific goals drive the December observation's size determination. Using thermal infrared measurements, we can separate reflected sunlight from emitted heat and calculate the actual diameter of the nucleus more precisely than brightness-based estimates allow. Detailed spectroscopy. What molecules are present in the coma? Not just major species, but trace compounds that reveal formation conditions and chemical processing. Rotation state analysis. Has the spin changed from perihelion? Outgassing changes in rotation provide information about mass distribution and structural properties. Search for fragmentation. High-resolution imaging will show if the nucleus split into multiple pieces under perihelion stress. Coma structure mapping. Where are the active regions? How does outgassing vary? Across the nucleus, jets, fans, spirals all tell us about subsurface structure. March the 16th, 2026, Jupiter flyby. The last major milestone before 3I Atlas leaves the inner solar system. The comet passes within about 54 million kilometers of Jupiter. The giant planet's gravity will bend the trajectory slightly, a final gravitational handshake before the visitor departs. NASA's Juno spacecraft in orbit around Jupiter will observe. Juno has ultraviolet spectrographs that can analyze the comet in wavelengths invisible to human eyes. It has a radio antenna that can listen for electromagnetic emissions, and it has cameras capable of capturing 3I Atlas against Jupiter's immense cloudscape. What makes the Jupiter flyby particularly interesting scientifically is the distance from the Sun. At Jupiter's orbit, about 5 astronomical units, solar heating is minimal. Any outgassing will be driven by internal heat or extremely volatile materials, carbon monoxide, nitrogen, things that can sublimate even when it's very cold. If 3I Atlas is still active at Jupiter distance, it tells us the comet contains material more volatile than anything commonly found in solar system comets. Europa Clipper. Unexpected opportunity. There's one more observation opportunity that few people are talking about but could be scientifically significant. NASA's Europa Clipper spacecraft launched in 2024, and en route to Jupiter's moon, Europa will fly through 3I Atlas's ion tail. Not the dust tail that consists of solid particles pushed by solar radiation pressure. The ion tail electrically charged gas molecules swept away by the solar wind. When a spacecraft flies through a comet's ion tail, it directly samples the particles and gases. Europa Clipper wasn't designed for comet studies, so it lacks dedicated dust analyzers or mass spectrometers optimized for cometary material. But it does have instruments for detecting charged particles, measuring magnetic field variations, analyzing the plasma environment. If 3I Atlas's tail has unusual properties, Europa Clipper might catch them. This is serendipity at work. Spacecraft that happen to be in the right place at the right time, contributing observations they were never designed to make. What we're building here is unprecedented. Multiple spacecraft at different locations, ground-based telescopes coordinated worldwide, amateur astronomers contributing observations, all focused on a single object for an extended observation campaign lasting months. It's network astronomy on a scale rarely achieved, and it's all focused on an object that will leave our solar system permanently within a few years. Once 3I Atlas crosses beyond Neptune's orbit, once it fades from view of even our most powerful telescopes, it's gone. In a century, it'll be light years away. In a million years, it might pass through another star system where perhaps other astronomers will point their instruments and wonder where it came from. This moment, late 2025 through early 2026, is humanity's only opportunity to study this particular visitor. The observations we make now are permanent. The data we gather will be analyzed for decades. And perhaps most importantly, every measurement contributes to our understanding not just of 3I Atlas specifically, but of the population of interstellar objects generally. Because 3I Atlas is not unique. It can't be. The mathematics don't allow it. If we've detected 3 interstellar objects in 8 years, and our detection capabilities are improving rapidly, that means hundreds or thousands of these objects pass through the inner solar system every year undetected. Too small, too faint, or on trajectories that don't bring them close enough for discovery. The space between stars isn't empty. It's littered with debris from planetary systems, ejected planets, rogue comets, all the cosmic cast-offs from billions of years of stellar and planetary evolution. 3I Atlas is our window into that population. Every measurement refines our understanding of what interstellar space contains, the Vera Sea. Rubin Observatory, which began operations in 2025, is expected to discover dozens or even hundreds of interstellar objects over the next decade. Each one will be a data point. Each one will help us understand, and each one will carry with it the possibility, however remote, of surprises we can't yet imagine. The observations scheduled for the next 6 months aren't just data collection. Their exploration in its purest form, reaching beyond our solar system without leaving it, studying samples delivered to us by the universe itself. Whether 3I Atlas turns out to be completely mundane or reveals unexpected mysteries, the process of studying it is pushing the boundaries of what we can observe and understand. That's what comes next. Not necessarily answers, but better questions. More refined mysteries, a clearer picture of what we know and what we still need to learn about the cosmic neighborhood we inhabit. The real story of 3I Atlas is only beginning. As 3I Atlas races back toward interstellar space at 68 kilometers per second, carrying with it the warmth it absorbed from our sun, we find ourselves in a peculiar position. We've witnessed something unprecedented, a comet that brightened more rapidly than models predicted, that glowed blue when it should have appeared red, that exhibited 8 distinct anomalies while simultaneously behaving naturally in every fundamental way. We've explained most of what we saw. The anti-tail was CO2 sublimation. The composition reflects an exotic formation environment. The structural integrity suggests unusual properties, or perhaps just larger size. Each anomaly has potential natural explanations, some more satisfying than others. We've ruled out the extraordinary scenarios. No maneuvering at perihelion, no signs of artificial origin, no evidence of technology masquerading as nature. The acid test came back negative for artificiality, and yet, in the careful qualifications of the scientific papers in the remains unclear, phrases in the brightness surge, and impossible color, there lingers something we don't fully understand. This isn't failure. This is the frontier of knowledge. This is where science becomes most interesting, not in confirming what we already know, but in confronting what we don't. Let's sit with that discomfort for a moment. In our age of instant information of AI that can answer any question of search engines that retrieve knowledge in milliseconds, we've become unaccustomed to uncertainty. We expect answers. We demand explanations. We're impatient with mystery, but the universe doesn't operate on human timescales or human preferences. It presents phenomena. It offers evidence. It leaves interpretation to us in our own time with our limited understanding. 3i Atlas presented itself on July 1st, 2025. We had 4 months to prepare. We threw everything we had at it: ground-based telescopes, space-based observatories, spacecraft positioned throughout the solar system, amateur observers coordinating globally, professional astronomers allocating their most precious resource time. We gathered more data on this object than on any previous interstellar visitor. Thousands of images, hundreds of spectra, continuous tracking of position and brightness. The data set is unprecedented in scope and quality. And still, after all that effort, after all that observation, some questions remain unanswered. Why did it brighten so rapidly? Why was the color so blue? What exact combination of composition and structure produces these characteristics? These aren't trivial questions. They're not merely gaps in our knowledge that better models will fill. They're genuine puzzles that suggest our understanding of comets, even natural ones, is incomplete. 3i Atlas came from another star system. It formed billions of years ago under conditions unlike anything in our solar system. It traveled through interstellar space for millions or billions of years, bombarded by cosmic rays drifting through molecular clouds, experiencing an environment that no object in our planetary system has experienced since our sun formed. The surface we observed at perihelion is a record of that journey. Every crater, every ice deposit, every dust grain carries information about where it's been, what it's experienced. The interior is a time capsule from another world, preserving chemistry from an epoch and place we can never directly visit. Think about what that means. This object is a messenger carrying news from beyond our cosmic neighborhood. Not intelligent news, not a message in any deliberate sense, but information nonetheless. Chemical signatures, isotopic ratios, structural properties, all encoding the conditions of its formation and its journey.
We're reading that message as best we can. Spectroscopy tells us about molecules. Photometry reveals brightness changes. Astrometry tracks position. Each measurement is a letter in the message, and we're learning the alphabet slowly, painstakingly. But we're not fluent yet. We can read some words. We can guess at others. Some passages remain cryptic, requiring more context, more comparative samples, more experience with the language of interstellar objects. The chemistry is a sample from a different star's formation environment. Our sun formed from a specific molecular cloud with specific composition at a specific time in galactic history. Every star forms from slightly different raw materials. The ratios of elements, how much carbon versus oxygen, how much silicon versus iron, vary. These variations propagate through planet formation. They affect what ices condense in the protoplanetary disk. They determine which molecules dominate in comets. They create diversity we're only beginning to appreciate. 3i Atlas is one data point in that vast parameter space of planetary system chemistry. It shows us that somewhere out there, perhaps billions of years ago, a molecular cloud with high carbon content collapsed to form a star and planets. In the cold outer regions of that system, comets formed with more CO2 than water, the opposite of what happened here. One of those comets was ejected, perhaps by gravitational interactions with a giant planet, perhaps during the chaotic early days of planetary formation when collisions and near misses were common, perhaps later as the planetary system evolved and orbits shifted. However it happened, this object was cast out into interstellar space. It began a journey that would span millions of years and vast distances. It drifted through the galactic disk, passing other stars at distances of light years, never close enough to be captured, but always subject to their gravitational tugs. Cosmic rays bombarded it constantly. High-energy particles accelerated by supernovae, by pulsars, by processes we still don't fully understand. Each impact was tiny, but over millions of years, millions of impacts, the cumulative effect was substantial. Surface chemistry altered. Crystal structures damaged and reformed. Volatile materials slowly lost to space. It traveled through molecular clouds, vast nebulae of gas and dust between the stars. In those clouds it collected new material, accreted a thin layer of the cloud's composition onto its surface. Different clouds have different chemistry. Each passage through a cloud added a new layer to the palimpsest of the comet's surface. And then after all those millions of years of wandering, after crossing distances we can barely comprehend, it entered our solar system. The discovery was accidental, as most discoveries are. A telescope in Chile doing routine survey work noticed an object that didn't belong. Further observations confirmed it was moving too fast on the wrong type of orbit. Interstellar. Word spread quickly through the astronomical community. Observing campaigns were organized. The object was studied intensively, more so than any previous interstellar visitor. And now, as it departs, as it accelerates back toward interstellar space, under the sun's gravitational slingshot, we're left with this strange mixture of satisfaction and frustration. Satisfaction because we learned an enormous amount. We confirmed its interstellar origin. We measured its composition and found it unlike our comets. We tracked its behavior through perihelion and saw unprecedented phenomena. We ruled out artificial origins convincingly. Frustration because mysteries remain. Questions persist. The blue color at perihelion, the rapid brightening, the exact mechanisms behind what we observed. But perhaps this is exactly as it should be. Perhaps the universe is telling us something important through this mixture of answers and continued questions. It's telling us that our sample size is still too small. 3 interstellar objects, Oumuamua, 2i Borisov, and now 3i Atlas, are not enough to characterize the population. We need dozens, hundreds, thousands of observations before we can confidently say what's normal and what's anomalous. It's telling us that natural phenomena are more diverse than our models capture. We built our understanding of comets from solar system samples, but the universe contains billions of planetary systems, each with unique chemistry. Our models need to expand to accommodate that diversity. It's telling us to be humble, to acknowledge the limits of our knowledge, to resist the temptation to claim certainty when we have only probability, to say, "We don't know yet," without shame or apology, because not knowing is the beginning of learning. And perhaps most importantly, it's telling us to keep watching, because 3i Atlas is not unique. It can't be. The mathematics don't allow it. Somewhere out there right now, another interstellar object is approaching our solar system. Perhaps it's already past Jupiter, still too faint for our telescopes. Perhaps it won't arrive for years or decades, but it's coming. And the next one might be even stranger than 3i Atlas, even more challenging to explain, even more likely to make us question our assumptions.
Or perhaps the next one will be boringly ordinary, confirming that 3I Atlas was an outlier, an unusually extreme example of natural diversity. Either way, we'll be watching, with better instruments than we had for 3I Atlas. The Vera C. Rubin Observatory, now operational, will scan the entire visible sky every few nights, sensitive to much fainter objects than previous surveys. We'll discover interstellar visitors, earlier track them longer, gather more complete data sets. The James Webb Space Telescope has years of operational life ahead. Future interstellar objects will receive the same detailed spectroscopic analysis that 3I Atlas received, building a library of compositions from across the galaxy. New missions are being planned. The Comet Interceptor. A European Space Agency project is designed specifically to visit a long-period comet or interstellar object. It will launch to a parking orbit and wait. When a suitable target appears, it will intercept, deploying sub-probes to study the object from multiple angles, perhaps even sampling material directly. Imagine what we could learn from an actual sample return from an interstellar object. Not just remote spectroscopy, but actual laboratory analysis of material from another star system. Mass spectrometry revealing isotopic ratios. Microscopy showing mineral structure. Chemical analysis determining exact composition. That's the future we're building toward. Each observation of each interstellar object moves us closer to comprehensive understanding. But understanding is a journey, not a destination. The more we learn, the more questions emerge. That's not frustration, that's progress. 3I Atlas showed us something we've never seen before. We've explained most of it. The rest remains unclear. And in that uncertainty, in that gap between observation and complete understanding, there's beauty. There's the beauty of nature being more complex than we imagined. The beauty of the universe presenting challenges to our intellect. The beauty of questions that resist easy answers. We're so accustomed to having answers instantly available. But some questions require patience. They require more data, more observations, more time to think and analyze and discuss. 3I Atlas is teaching us patience, teaching us to sit with uncertainty without anxiety, teaching us that not knowing is not failing. It's the natural state of science in progress.
So here's the question that will linger long after 3I Atlas fades from view. The question that matters more than whether this specific comet was natural or artificial. In a universe with billions of star systems, each potentially harboring chemistry and physics, we've never encountered each with its own unique formation history and evolutionary path. In such a universe, how do we know we'd recognize something truly extraordinary if it passed through our solar system? What if the real mystery isn't whether 3I Atlas is natural or artificial, but whether we even have the conceptual framework, the theoretical understanding, the observational tools to tell the difference? What if nature at its extremes looks so strange, so unlike our experience that it becomes indistinguishable from the impossible? What if the blue glow at perihelion, the rapid brightening, the 8 anomalies compounded? What if these aren't the solution to the mystery, but the articulation of a deeper question we haven't yet learned to ask? 3I Atlas is leaving. Every second it travels another 68 kilometers away from the sun, away from Earth, back toward the vast emptiness between stars. In a few years, it will cross Neptune's orbit. In a few decades, it will be farther from the sun than Voyager. In a few centuries, it will be truly interstellar again, unreachable by any technology we currently possess. And it will continue its journey for millions more years, perhaps billions, until perhaps it enters another star system where perhaps other beings will observe it and wonder where it came from. What will its surface look like by then? Will our sun's heating have altered it detectably? Will some observer, trillions of miles and millions of years from now, see chemical signatures and understand that this object once passed through our solar system? We'll never know. This is a one-time encounter, a brief intersection of trajectories, a momentary alignment between this ancient wanderer and our small blue world. But the questions remain.
The data remains, the challenge to our understanding remains, and perhaps that's exactly as it should be. Perhaps the universe is supposed to present us with puzzles we can't immediately solve. Perhaps the discomfort of not knowing, the tension between what we observe and what we understand, is precisely what drives us to look more carefully, think more deeply, question more rigorously. We saw something we've never seen before. We've measured it, analyzed it, debated it. We've explained much. We've acknowledged what remains unclear. We've ruled out the extraordinary explanations. We've confirmed it obeys natural laws. We've maintained scientific rigor while remaining open to possibilities. And in doing so, we've demonstrated something important about humanity. We're ready.
Ready to find something genuinely extraordinary if it appears, ready to investigate carefully, ready to follow evidence wherever it leads. Three-Eye Atlas wasn't that something extraordinary. It was natural, unusual, but natural. But someday perhaps something extraordinary will pass through. And when it does, we'll be watching. With better instruments, with more experience, with the hard-won wisdom that comes from carefully examining the merely unusual and distinguishing it from the truly impossible. That's the legacy of Three-Eye Atlas. Not that it was aliens, not that it was mysterious beyond understanding, but that it taught us how to watch, how to question, how to maintain the delicate balance between skepticism and openness. The comet continues its journey, but ours continues too. The journey toward understanding our place in this vast cosmos, toward knowing whether we're alone or merely one among many, toward comprehending the full diversity of nature across billions of light years. We're not there yet. We have far to go. But we're watching. We're learning. We're ready for whatever comes next. And something will come next. That's the one certainty in this story of uncertainties. Another visitor from the stars is already on its way. Whether it arrives next year or next century, it's coming. And when it does, we'll be here looking up, ready to see what the universe wants to show us next. That's the final lesson of Three-Eye Atlas. Not that the cosmos holds easy answers, but that it rewards those patient enough, curious enough, persistent enough to keep asking questions, even when, especially when the answers don't come easily.